Thank you very much to the presenters and the audience for being here today. This is our third doctoral meeting session. It's a quite exciting session on again, electric propulsion for space environment. And we'll be having today 7 presentations by Maria Sherezade, Celia Mboye, David García La Huerta, David Madaloni, Víctor Gómez García, David García Villegas, and Borja de Saavedra. Basically, we're going to be today listening to 3 presentations on the Zarathustra Starting Ground project that Mario presented to us in March, and you have the presentation and the recording should you want to check what he's proposing. So it will be a good opportunity to listen to his project. Maria will be presenting her thesis on Micropulse plasma thruster design. So again, an experimental PhD thesis, very interesting one. And then we'll be hearing to 3 industrial PhDs with CENER and ENI Space. ENI Space indeed is a spin-off of some research that was done in EP2 group 2-3 years ago. So it's very interesting also to see what we are being able to transfer to society in the form of a spin-off and new positions for people and groundbreaking research. As you know, the presentation should be 10 to maximum 15 minutes long, right? So keep an eye on the time. We will be strict on the time, right? Because then we'll need some minutes for questions.
Okay, so hello everyone. I'm Francisco Borja de Saavedra. I'm also an industrial PhD student in ENI Space as David, and I'm here to present the sizing and direct characterization and simulation of externally wetted ionic liquid electrospray thrusters. My thesis director is Daniel Perez at ENI Space, as Manuel mentioned before, and Pablo Fajardo at UC3M. Okay, so give me a second. Okay, so let's start with the problem motivation of this thesis and the industrial R&D project of ENI Space as a whole. So first of all, it is clear that carrying an onboard propulsion system increases the functionality and versatility of the mission, from essential maneuvers like station keeping to unlocking new possibilities and objectives, apart from helping to contribute to a sustainable space environment by means of deorbiting and collision avoidance maneuvers. Despite these benefits, when we look at the growth of the nanosatellite market, we see that actually very few of them carry propulsion on board. So in fact, while larger spacecraft typically do so, the propulsion adoption rates in pico and nanosatellites is less than 6%, leaving them with no maneuverability, less functionality and revenue per platform, and potentially higher mission costs. So this is the motivation of this thesis and the project at ENI Space, that is like to cover that research gap, let's say, and eventually commercial gap. So yes, and the state of the art is basically that well, it is necessary to understand the reason behind the low adoption rates of propulsion in the smallest satellites. We have identified that mainly 3 of them. That is basically, first, the variability of the platforms, that they can change across 2 orders of magnitude in terms of mass, power, and volume. So it is clear that a one-size propulsion system doesn't fit all, and there is a bit of a lack of scalable solutions in the market because of these constraints in power, mass, and volume. And we have seen that there's also a lack of, let's say, dedicated knowledge in terms of the coupling of propulsion and orbital dynamics. So there's a lack of specialist profiles, especially in small teams. So our approach at ENI Space is to bridge propulsion and mission design with hardware and software. We are, as David said, we are developing Athena, the adaptable thruster based on electrospray for nanosatellites, that is meant to be a fully customizable propulsion solution designed through concurrent engineering and mission analysis with our novel tool ENI Go. I will talk a bit more later. So the idea of this thesis is at the core, let's say, of the project of ENI Space, is to provide tailored propulsion solutions. So instead of seeing what you can do with a given propulsion system with fixed, let's say, more or less fixed overall parameters like other solutions, our approach is to provide a tailored solution by solving the inverse problem. So for a given platform and maneuver requirements, find a custom optimum propulsion system for your particular mission. So now that I've explained the problem motivation and kind of the project as like overall, let's move on to the particular objectives and the procedure to be followed in my thesis. So first of all, a preliminary mission analysis tool is to be developed to study the variability of the propulsion parameters in terms of platform constraints and different operational requirements in different scenarios, but mainly focused on low Earth orbit. And from this, the idea is to determine the starting point of the design of a scalable thruster based on externally wetted ionic liquid electrospray technology. So let's say that like the eventual version of Athena. In parallel to this, direct diagnostics are going to be designed and developed in order to measure thrust and propellant consumption for the characterization of the first prototypes that have already been developed by Aerospace. So from the results of the tool and the testing campaign of the first prototypes, the best combination of manufacturing and operational parameters will be obtained. So a sizing will be done for the next generation of thrusters. And these will also be characterized in terms of performance, like afterwards in a new test campaign. Also, scaling laws of this type of electrosprays will be studied towards adapting the propulsion system to different platforms and mission scenarios, as those studied with the preliminary tool. So the idea is to cover as much ground as possible. Finally, the behavior of the thrusters could be studied through multi-physics simulation in order to keep improving the propulsion system in future versions and compare with the experimental results and do parametric analysis also for future versions. So this is mainly what we'll be doing in my thesis. Since I started in November, I already have some results. First of all, the first version of this concurrent mission propulsion system design tool, which is the ENIGO that I mentioned before, has been accomplished. It has been done so by following a secular propagation approach. So it uses simplified dynamics to allow for multiple constraint optimization of maneuver duration or propellant mass. It has been benchmarked against GMAT. You can see an example here in the figure. That is basically just a change of inclination, and you can see that the ENIGO fits like GMAT results. And if you zoom in, you see like the GMAT has like higher order perturbations that we avoid in kind of like ENIGO. So we are kind of trading these short-term effects for computational speed. For now in ENIGO, we use the propulsion, well, the expected propulsion model of Athena, of the first Athena thrusters, with variable specific impulse, but the results of the tool can be extrapolated to other solutions. So basically, ENIGO, the input it takes is, as I said, for a given platform, the constraints the user wants to give to the propulsion system, the starting point or the initial orbit, and what are the maneuvers and the constraints to them that you want to have. And basically, the core of ENIGO is a propagator that is wrapped in inside a solver routine to fit to match the maneuver duration that the user wants. And everything is wrapped in an optimization layer to get the best results. So the actual output of ENIGO is not just like the maneuvers, but the optimum thruster and operating point and all the propulsion parameters for that particular case. So I have recently presented this tool in the ESA CubeSat Industry Days, in case you missed it, upon the release of the beta version. And we have made it open access for the space community. But basically, what for the PhD, let's say we care about the backend, so that the actual computation of ENIGO that I will be using for the objectives that I've set and that I will comment on later for the next steps. So regarding the direct diagnostics, I have also started doing something. We have adapted an analytical balance that we have for operation in vacuum. we have this preliminary, very preliminary setup that we have mounted on the medium-sized chamber at UC3M at the EP2 laboratory, and it seems to operate correctly. So we have just done this first setup and tested it. Not let's say insightful results yet, but yes, the setup and the test procedure improvements are also underway. And of course, I will be working in close collaboration with David, as he mentioned. Okay, so what are the next steps in my thesis? Basically, here you can see in green what is partially done or in progress, and in orange what is going to be in the next steps. So about the concurrent preliminary design tool, that was kind of like the first objective, that is ENI Go. As I said, it's already like working. You can actually, if you want, to register at go.eni.space in the beta version. We appreciate all the feedback we get. But yeah, I want to do a lot of improvements to the tool, also to generalize it for different propulsion systems in order to study different platforms and mission scenarios. Regarding the direct diagnostics, as I said, I have a very preliminary setup, but I expect also in regeneration to characterize the performance of these first prototypes of Athena through thrust and propellant consumption measurements. And as he also said, we have a joint presentation at MPCS about this characterization. And in the next year, I will also start like this sizing and performance characterization of the next generation thrusters. Basically, the sizing, as I said, our idea is to do kind of concurrent engineering. So based on the results of our tool and what the users in the nanosat market want, try to put that into the, let's say, the workflow of the development of the next thrusters. And after that, of course, we will be doing more test campaigns to characterize that. About this simulation, it's not planned at least for next year, so probably for the last one, and we will see depending on how the concurrent design and the diagnostics go. But well, yeah, as I said, we will see. So thank you very much. If you have any questions, so just ask.